Hello everyone, it's my great pleasure to introduce Amritha Raghunath. Amritha is a software engineer who spent the last decade at Meta, focusing on data privacy and user safety. She holds a master's from Stanford University in computer science. She originally hails from India, finishing her undergrad degree from the National Institute of Technology, majoring in computer science. Amritha has worked briefly in major technology corporations such as Box and Microsoft prior to her tenure at Meta. Today, she is going to talk about purpose limitation at scale with privacy-aware infrastructure. Thank you, Amrita, for accepting our invite. The floor is yours.
Hello, everyone. I think as Professor Hadi just mentioned, I will be talking about purpose limitation at scale with privacy-aware infrastructure. I know that's a mouthful and there's a lot to cover, and I promise I'll get to that. Okay, with that, like you mentioned, I'll first introduce myself. I'm Amrita. I'm part of the Instagram privacy team. I've done a lot of work on user safety, privacy, and so on. That's where I spend the majority of my time at Meta. I've also worked at a few other teams, so if you guys want to talk about that at some point, I'm happy to discuss that as well. We have a lot to cover, so I'll just get into the topics today. So I'll begin with the outline. So we'll touch a bit on what is purpose limitation. We'll talk through some of the key challenges, especially that we face, and Meta's approach on how we've tried to address this. And then finally, we'll take a look at policy zones, which is how we are enforcing purpose limitation at Meta. So we'll begin with some context. Meta has various privacy requirements. Many are related to purpose limitation. Of course, that is not the only thing we do. And purpose limitation essentially means to ensure that data is or is not used for some stated purpose. You can also just Google for purpose limitation, and I just put a screen grab of whatever Gemini says. Purpose limitation is very top of mind for a lot of regulators also, as we're getting more and more into the digital age and a lot of information is just available outside. Purpose limitation under GDPR means that personal data can only be collected and used for specific, explicit, and legitimate purposes, and cannot be further processed in a way incompatible with those original purposes. And here you can see that there are a lot of examples that are being presented on data, users' personal data was collected for one reason and then ultimately was used for some other purpose. So we look at this with some examples. Let's say we have a requirement related to banana data. And for the rest of this talk, we'll focus on everything in this toy example world where banana data is a user's personal or sensitive data, and we don't want to use it for just anything out there. So there are two ways that purpose statements are phrased. Sometimes it's in the positive, like in this case, we're saying banana data is only used for smoothie making purposes. Another way is sometimes in the negative, where we want to be very specific that some data shouldn't be used for certain purposes. So for example, banana data is not used for bread making purposes. And let's consider this as our main purpose statement that we're going to go with for today. There are three key challenges to highlight when solving purpose limitation. There's limited prior art in the industry. The scale and diversity of Meta is just huge. And finally, the granularity of representation is also very confusing. Rolling out purpose limitation on data on existing code and systems is fairly novel in the industry and does not have established techniques and processes. Existing privacy controls at the company and well, even at the industry solve the problem of who can access data. Technologies like auth tokens, user identity, and even ACLs do this quite well and have been around for years. There's nothing new over there. They prevent one user from reading the private data of another user. However, this is completely unlike the new problem that we're solving. What can access the data, where, and for what purposes? my phone is sending out hundreds of requests to Meta servers for a variety of purposes. If we went with the WHO-based privacy, we would allow all of these uses. It's my data and it's my phone. So I'm the WHO, and so everything should be allowed. Purpose limitation requires us to build a new framework that only allows some requests to access my banana data. So again, in this example, my banana data can be used for smoothie making purposes or maybe to build a fruit basket, but we don't want to use the banana data for bread making purposes. Ensuring the safeguards work consistently across various languages, runtimes, and types of workloads and at meta scale is not easy. So just to put this into some perspective, we have 3 billion or 3 billion daily active users. This essentially means we have a massive request volume flowing through our servers. We have millions of assets. Assets is another terminology I will be using quite frequently for the rest of the talk. And so what we're referring to as assets is any chunk of data. So it could be a MySQL table, or it could just be a row in a table or some other data store. But we also call code or pieces of code also as an asset over here. So think of like a function as a granular code asset, or something as big as a web request or a service as well. But essentially, the point I'm trying to make here is that we have millions and millions of assets, so the scale is high. We have a multitude of data systems and languages and APIs. So think of most popular languages. We definitely have them at Meta. So C++, Python, Hack, Java, JavaScript, Rust, so on and so forth. So the complexity associated with handling all of them is also pretty high. And we have various kinds of workloads. You have offline or batch processing jobs. You have like online web serving. You have machine learning training, logging, a lot of very, very different kinds of workloads as well. And another interesting thing at our scale is that code pushes continuously throughout the day. And we don't have like a cutoff, and then we don't like sit and check everything. We have a continuous push. So it's not really feasible for us to stop every push and check for privacy. Another way to look at our scale is from the people angle. We have more than 50,000 employees. Not everyone should be a privacy expert. And a single request often passes through multiple teams' ownership. So for example, here, if you look at the banana smoothie request, you have one portion of the request being handled by the banana UX team. Parts of the code and the requests are handled by the fruit storage team. Data goes to the warehouse, there's a ranking team, there's a smoothie infra team, and so on and so forth. So the single request passes through multiple teams' ownership. And requirement owners are often not product experts. So when I speak about requirement owners, they're usually privacy teams embedded in different like big products that or flagship products that we offer, right? And these requirement owners need tools to help them understand how the data is flowing through the system. And if all of this wasn't messy and complex enough, we also have different teams producing and consuming data that we have. So data producers and data consumers are often different entities, meaning there's no single point of contact for what do we need this data for. And then let's get into the granularity. Data and scope may be present at different levels of granularity. This makes precise tracking and enforcement challenging. So we spoke a bit about how there's no single team that knows who's, what are all the use cases of the data, but we also have data available at different granularities to do the tracking. So for example, a given table may be entirely banana data. Or if you look at the second example, you have an ice cream or a sundae table where just a single column has banana data. You could have a mixed data table, like a fruit table, where some rows are about other fruits and some rows are about banana. Or you could also have a case where only a few cells have banana data as well. The granularity also applies to code assets. So for example, you have multi-tenant services or frameworks that take in different types of data through a common choke point. For example, here, banana is not being used for bread purposes, but they're both passing through the store food function. This function sometimes has banana data and sometimes does not. Even if you look at the second example, you see that the make breakfast function, a part of the request actually goes through make smoothie, which does deal with banana data, and then the other part actually does not deal with banana data. With that, let's get into Meta's approach. Previously, we described some of the challenges. Now we'll talk through how we're going to solve it. Here, I'm going to talk about the workflow from the perspective of a requirement owner. Again, a requirement owner is like a privacy team that's embedded into each of the product groups that we have. The requirement owner is responsible for the technical implementation of a given requirement. This is typically, again, a different person than those that own code and data assets. The overall approach for purpose enablement is pretty straightforward. Step one, we find the banana or discover all the assets which contain banana. Next, we look at the data flows, or essentially see where the banana data goes. Step three, check uses of banana. So we check if, hey, banana data is flowing here, it's being used here, is it an acceptable use case, or do we want to remediate, and so on. Finally, we go into a step 4, which is to prevent future banana misuse. And the last step is to make sure banana use protections continue to work all the time. It sounds simple, but achieving it can be a lot of work. So let's look at each of these steps a bit more. Discover assets. That's the step 1. So here we're trying to find the banana. And this can involve many different techniques. In some cases, all we look at is like, oh, that table is called banana data. Sometimes we have systems that scan for particular patterns and logs. Sometimes we use a classifier to tell us if each of these assets have banana data in them. Once we find the banana candidates, we can then review and annotate them. This process is usually mostly automated based on scoping rules. And then there's a small few candidates that we might have to do human reviews for. So the first step here is to find what we call the seed assets that contain banana data. Once we have the seed assets, we now start looking at the flow of data everywhere. So one thing that we do often is that we look at everything as a flow of data, which means you have a starting point and an ending point. And the start point of the data is called the source, and the endpoint is called the sink. So there are 3 scenarios for us to consider once we have our seed assets, which have been marked as containing banana data. First, we have a data flow from an unannotated asset. So essentially, we don't know if this asset has banana data or is allowed to process banana data. But we see that data is flowing from this asset to an asset that is marked as can process banana data. This is okay. We don't think that it's doing anything with banana data. So we think this is okay, and we don't have anything to do further over here. The second one is we have data flows between assets that are annotated as banana. So both sides are claiming that they can process banana data. So that is okay as well. The third case, we have a data flow from a banana asset to one that is not. So this is the important case that we want to actually follow up on. And this needs to be reviewed. So let's look at how we would remediate this. There are 3 ways that we could go about this. Option 1, the sink asset is allowed to use banana data, or it can also process banana data. In this case, we just go ahead and add the banana annotation to the sink asset as well. Option 2, we find that while the data flow exists, actual banana data is not being used. This is an example of where we would say that the banana, the sensitive data has been removed, or we're desensitizing the data, or we've sufficiently anonymized the data depending on the context. So in this case, we feel confident that it's okay to drop the banana annotation, and we refer to this as reclassification. And finally, we find that the sink is actually part of, say, bread making. And in this case, the data flow needs to be broken or needs to be stopped. So as we can see here, this is a little bit of a recursive process. We start with seed assets, and then we look at all the cases where data is flowing from a seed source asset to a sink. And then for each of those data flows, we decide how to remediate. In this case, when we either reclassify or remove the data flow, there's not much to follow up on, but every case where we go and mark the sink, also containing banana data, we are now introducing new data flows where the source is banana, and there are a bunch of other unannotated sinks. So we do step 2 and 3 in repeat until we finally reach a state where there are no new data flows. In step 4, we prevent new potential banana misuse from occurring. We have built a variety of techniques that span checks at code change or at diff time to active blocking of such data flows during program execution runtime. So we've also implemented different ways of catching this. Obviously, earlier is better, but in the worst case, we will catch it in production at runtime. The final step is then to ensure that the banana use remains as intended. New banana sources and data flows are discovered and remediated. Invariants around reclassifications are maintained, and any additional or out-of-band checks pass. Example, we may actively inject test bananas and look for them inside the bread factory. All of these steps together ensure we can use bananas as intended. And with that, let's go into how we manage the data flow violations. Let's dive deeper into what we do over here. As we mentioned previously, a core part of our approach is managing data flow violations, detection, remediation, and prevention. At Meta, we've developed a new technology to help us for these phases. So policy zones is what I'm going to be talking about to cut to the chase a bit, but that essentially covers these 3 steps. We have different pieces of tooling and infrastructure that we've built to support the discovery and the continuous monitoring cases. We mentioned earlier that purpose imitation is still nascent. And when solving the purpose imitation problem, Meta had to develop something new, essentially to differentiate ourselves from the user-based access to purpose-based. Where can the data go? Where can it be used? And this is what we call as policy zones. We touched on this a bit earlier, but policy zones essentially looks at everything in as a data flow. So our main important unit to look into is data flows. A data flow is any read from a data store into code or a write from code to a data store. We also consider everything else as a data flow when data moves across code boundaries. So think of an RPC call where the client is sending data to the server that is also considered a data flow. But you can also look at more granular cases where you have a function call within the same process, and that is also sending data across the function boundary. We also consider this as a data flow. So essentially everything is a data flow over here. Policy zones is based on information flow control theory. Information flow control theory is not a new concept. It has existed since, I think, the 70s or 80s. It is a security concept that focuses on managing how information is allowed to move within a system, ensuring that sensitive data does not leak to unauthorized areas by defining strict rules regarding data transfer between different security levels. Essentially, preventing information from flowing from a higher security level to a lower one without proper authorization or mitigation strategies. So this is some of the examples of how policies look in this case. We have different types of policies that you can configure. The only constraint that we have is that the policies need to form a mathematical lattice. So in this case, we're looking at the can use banana policy. This is one of the most simple policies that we can develop. And over the years, we have discovered that policies that have or policy lattices that support many, many different nodes in them actually get a little bit more confusing. And we reserve them for more complex use cases. And for the more simple use cases, we just use the Boolean on-off. Can use banana is off is one state. Can use banana on is a different state. Another standard example that you will find if you read some of the information flow control theory research papers is the FBI clearance example. So in this case, you see that a file that has been marked as confidential can flow into the hands of an agent who has secret as his security clearance. But the opposite is not allowed. A file that has been marked as top secret cannot flow into the hands of an agent who only has secret or confidential clearance. Another thing that I'll touch on is, but in some cases, if you desensitize or remove any highly sensitive information, and you can redact important things, you can declassify or reclassify it and still allow the data to flow into the hands of an agent that has a lower security clearance. As we mentioned, everything is a data flow, and the main check that powers policy zones is the data can't flow. You start with a from policy and a to policy, and then you check whether that is acceptable. I wanted to touch a bit on meta scale. We do this data can flow check. I just checked this, I think like a week ago. We do this 5 quintillion times per day. I actually saw this huge number with so many zeros. I had to Google what number that actually maps to. And I learned, till now, I didn't even know there was a word called quintillion. But this maps down to 58 trillion checks per second. And this is only in one of our services. It is our largest web tier service. And we do all our other services are definitely lower in load compared to this. But even as I say that, this is just like one of those services. We have so many more services as well. So let's start with a toy banana data flow diagram and look at how we would go about using policy zones. Here, BananaDB has already been marked as containing banana data. Let's take a second to look into how this annotation actually looks. So in code, this is how it looks. BananaDB could be backed by any sort of like a storage system, but in Meta, we often have ORM models or object relational models on how we would represent it as an object at runtime. And this allows us to schematize everything. So we go to these schemas, and here we've added policy annotation to the schema. And we're saying that BananaDB is marked as can use banana policy. So now getting back to this example, we see that BananaDB is a source and banana request is the sink. And we see that there's a data flow violation from BananaDB to banana request. The request is reading banana data, but it does not have a can use banana annotation. In this case, banana request should have access. So we remediated by annotating it as can use banana. At Instagram, we use Django views. This type of annotation would differ depending on what system and what language you're using. For this talk, I'm mostly just focusing on how we do this in Instagram, but we have a lot of different pieces of infrastructure, and we actually support this kind of annotation everywhere. So in this case, we use Django views, as I mentioned, and you can see that we have a decorator over here on the API view. It says policy zone view, and it has a policy name, which is again can use banana. Okay, so great. We have the data flow between BananaDB and banana request in compliance, and everything looks good. But now there's a new data flow violation from banana request to log B. In this case, turns out that log B is only used for smoothie making purposes and to understand what's happening in debugging and so on. So log B can also be, log B is also allowed to use banana data. And we know that it's not being used for bread purposes, so we remediated by also annotating it. Again, in Instagram, much like other things, logging is also schematized. We have a logger schema. We go to the schema, we also slap it with a policy of can use banana. So great, now we have remediated all our violations. Everything is resolved. And at this point, what we would do is we would go from a logging detection mode in production to an enforcement mode. That's how we go into what we call as the state of prevention. This request is running in a banana zone. That's the terminology we use, that the entire request is running in a banana zone. I can enable enforcement for banana zone, as I mentioned, upholding the requirement over time without manual review or human-driven tools anymore. So when a developer adds a right to a non-banana data sync within banana request, it will be blocked by the infra. So for example, let's say there was a new logger that started logging data over here, and this logger is allowed to process and is ultimately being used for bread making purposes. In this case, since our banana request is already in enforcement mode, the log would just fail in production. In the worst case, and in most cases, it's caught well before we go into production, depending on the stage that we're at. So essentially, this becomes a self-enforcing system where teams either apply a banana annotation to their code or their assets. For example, if the team actually did want to support logging to log C, it would have to go and add a can use banana annotation, but then that would mean you'd have a lot more flows to remediate depending on everywhere that log C is being used. And so it becomes a self-enforcing system. So either teams can choose to add the annotation and be subject to additional restrictions, or they have to choose to lose access. But this is very coarse-grained, and I wish things were this simple. It works for a lot of the cases, but in most complex cases, only a small portion of the request is dealing with banana data. So let's look at this example. Here, the banana operation may be a very small operation of the entire request, called by the make banana smoothie function over here. So if we look at this again, there's another data flow violation to remediate now. Make banana is returning banana data to make banana smoothie. Since it's returning banana data, and we also think make banana smoothie should be allowed to access banana data, let's just go ahead to the next frame up the stack. So here, as you can see, we marked make banana smoothie as something that can use banana data. Now we have a different data flow violation to remediate. The data flow from make banana smoothie to breakfast request. Maybe a requirement now says a banana doesn't count as banana data anymore if it's blended with milk, spinach, some sugar. It's sufficiently desensitized. Or again, if you want to call back to the FBI clearance levels, we have redacted all the sensitive information, so it's okay for it to flow into the hands of an agent who has a lower security clearance. So in this case, we're saying that make banana smoothie isn't actually returning banana data, so we can reclassify the result. So that's what we do over here. We reclassify the flow instead of marking breakfast request as can use banana data. And now we have all our violations resolved. So to do this at scale, we're not actually labeling every function in the code base. That would be insane if we had to go to every single function and mark it as can use banana data or cannot use banana data. Really, we're just looking at the boundaries. Make banana smoothie is running in a banana zone, as are all functions below it that it calls. We propagate the zone through the stack implicitly. So a thing to notice over here is that we made an intentional design choice while building policy zones as to whether we want to explicitly send the policy or context information, or if we want to maintain it implicitly. This is pretty critical, and both sides have some challenges. If we went with the choice of explicitly passing things down, we would actually have to touch every function in the call stack. Starting from the first function, you'd have to create a banana zone information and then pass it down to every other function down the stack. Not only would you have to touch a huge number of functions that are being used, but another important thing to notice is that now we're allowing individual functions along the way in the call stack to tamper with this information. So that's another reason why we did not want to go down that route. And instead, we just maintain the context implicitly. So in make banana smoothie, we instantiate the banana zone, And that context is implicitly maintained for all the functions down the stack. I can enable enforcement for the banana zone now, just like I did for the request earlier, and prevent future data flow violations. So if log C or log D were happening in other parts of the same request, it would be completely fine. But if somebody tried to introduce a call to log C within the banana zone, we would still see a failure. We have a similar but slightly different marker construct to mark the function as being in the banana zone. So just to look at this example, like I mentioned, we only add this marker to the boundary functions. So in this case, you can see that the async make banana smoothie has a marker decorator, which says it's in a policy zone, and it has the can use banana policy. But what if make banana and make toast run through common multi-tenant infrastructure? So let's look at this case. We have a breakfast request, we have make banana smoothie, make toast, and you have make food, which is a common function that either makes a banana or a bread. FoodDB and LogDB have some rows, or like in some cases deal with banana data, and in some cases they deal with bread data. So what we do is essentially still the same thing. Just like before, make banana smoothie is running in a banana zone, and we propagate the zone implicitly down the stack. So what that means is when you're running make banana smoothie, we set the zone as being in a banana zone. And since the context is maintained, when you are running make food down the stack of make banana smoothie, we're fine. And we know that we're running in a banana zone. Whereas when you're in make food, which came from the make toast side of the world, we know that we're not in a can use banana data situation. Sorry. We propagate the zone to the data as well. So in this cases, if we have FoodDB where some rows are allowed to process banana data and some rows are not, we also propagate the zone to those rows, enabling the infrastructure to track which rows are banana and which rows are not. So with that, I think we've done an overall high-level overview of what we do with policy zones. And this was, while it looks simple, and it is hopefully easy to understand, there's a lot of complexity that goes into developing this. We started this several years ago, and we had to go through several iterations for us to land at a place that we felt comfortable enough to start in supporting several requirements using this infrastructure. So one of the things we definitely saw was how all of these different pieces of infrastructure, like data stores or data schemas or loggers, all of these support an annotation. It's not enough if we just go slap an annotation saying that, yes, it is subject to this policy. Somebody actually has to go enforce those annotations, and that's where the policy zone infrastructure comes. We built the policy zone's core functionality as a standalone library, and we've implemented this library in almost all the languages that we use. And from there, we've had to do integrations with all the pieces of infrastructure that we use at Meta as well. So just to call out some of the technical challenges that we have over here is just maintaining the activated zone implicitly. So to help contextualize this a bit, think of the cases where you have one part of the request doing some banana-related processing, and the other part is doing some bread-related processing. In Python, for example, you have an async IO event loop, and we start the make banana smoothie, and we put it into the banana zone. Now, if we were doing this at the request level, as in this case, it is much easier. We can just store the implicit zone or implicit information as a request global information. Hey, we're in the banana zone. So anytime we want to do some of these like data flow checks, we know that depending on the side of the data flow, for example, if we're doing a write, we just know that the from policy is banana zone, and then we just check the policy annotation on the data store. This becomes a bit complicated in maintaining the implicit context for cases where only a part of the request is running in the banana zone. So we start the make banana smoothie task. We instantiate the banana zone, but we cannot maintain this in global state. Because as we start doing some IO, for example, we're talking to BananaDB, most likely what Python is going to do is it's going to pause the task as we're doing IO and pick up the next task in the async IO event loop. In this case, that is going to be the make toast side of the world. And what is going to happen here is that we have to remember to pause execution of make banana smoothie while also saving the state that was running in banana zone. And as we go into make toast, we have to remember that we don't want the can use banana zone information activated. And again, as we pause make toast, we want to save the same state. And as we resume executing the task on the make banana smoothie side of the world, we want to resume the state that we're in a banana zone. That is one of the important challenges that we've had to maintain in terms of like implementation. Just to put it in perspective, this is going to happen several times, even in a single request, and this has to be highly optimized. Otherwise, we're going to risk seeing a huge compute cost to maintain these kinds of things. Not only compute, you can imagine a request processing latency would also regress a lot if we don't make this very, very performant. Another thing to remember is that we need the data stores also to operate at high throughput. A single request is probably doing several thousands of read and write operations. So the throughput is very, very high. And now, not only do we have to maintain the current state as we switch through the different tasks in an async IO event loop, we also have to implement the data can flow check every time data is flowing across boundaries. So we have a very high throughput, and we're integrating with very, very core or low-level infrastructure like writes, network operations, and so on. Again, just to remind, in our biggest monolithic service, which is our web service, we have 58 trillion data flow checks happening per second. Another thing for us to also remember is the developer experience. I touched on a little bit before that policy zones only work if your policy forms a lattice. We initially started with a very rich system of annotation of how people could add their policies and purposes for all of their assets. So you can go to your code asset and you can tag all the purposes. Oh, I can, this piece of code is used for making bread, it's used for making smoothies and whatnot. And similarly, this data asset contains banana-related information or apple-related information and so on, right? When we had a very, very rich way of annotating all these assets, we found that developers, the average developer does not deal with privacy requirements, and they found it very confusing to read and understand the code and walk around how all of these things were operating. And it was almost like a bunch of landmines that they would touch something, do something that they didn't understand, and were breaking things. So this is kind of where we started in, I think, like 2019 or 2020. But over time, we evolved it to, for most of the average use cases, we just need an on-off kind of label, which also fits the mathematical lattice requirement. So can use banana data off and can use banana data on is the easier case that we found works for most use cases. Of course, we still do have a handful of complex cases that are hand modeled with a slightly richer set of labels that we can annotate with. Another thing to remember here is remediation. So we spoke about how in some cases we can just automate the remediation where we know like, hey, this side is also allowed to use, this asset should also be allowed to use banana data. So let's just write some automation or build some automation tools to just go automatically slap them as containing banana data. But it becomes much harder when we start looking at the cases where we want to reclassify. So for example, let's say we're saying that since we are, blending a banana and adding spinach and milk and sugar and whatnot, that we have sufficiently anonymized the banana data as we're making the smoothie, and we can say this is reclassified. But today we need a way to mark something as sufficiently desensitized, and that changes a lot from context to context, and we have to programmatically enforce it. So a good example of where this can get very tricky is maybe today the code is in a state where a banana smoothie includes, like I said, spinach, milk, sugar, and all those kinds of things. So it's okay to mark it as a reclassification. But over time, let's say that the code keeps changing and evolving, and we remove the sugar. And then after some time, we remove the milk. And then maybe one day we also go remove the spinach. And all of these are done over a long period of time by different engineers on different teams. And we're finally in a state where we just have a plain blended banana. In that case, is it still okay to call it as sufficiently desensitized? Maybe, maybe not. So it's important for us to codify the requirements into code so that we can uphold it as we go, and we review these changes when the situation changes as well. This has been another pretty tricky area to do it at scale. Another tricky area has been leaks in the system itself. So we spoke about how in a bunch of these cases where the entire request, for example, is in a banana zone. That's, again, like one of the easy cases. The entire request is in a banana zone, so every single asset is essentially operating in a place where it is allowed to access banana data. However, we do have the case where a part of the request is allowed to access banana data, and a part of the request should not be accessing banana data. In this case, it's very possible that the make banana smoothie side of the world writes some sensitive banana information to a request global. And when we start implementing the make toast side of things, we might be accessing the same global, and that could mean that we unintentionally have access to banana data. So to overcome these kinds of things, and global is not the only way we do leaks. We could also have request params being passed by reference, for example, between make banana smoothie and the banana request. And if the same param is, and if the same object is then passed by reference to the other side, again, we could have access. To overcome this, we have actually developed updates to our type system itself. So we've introduced, for example, in Python and Hack type systems, the concept of a read-only type. This is not the same as a const, but it's where nobody can mutate it, but read-only allows certain places to mutate it if it has immutable references, and certain parts of the code to not mutate it if it has a read-only reference to the same object. So there was a lot of things that went into overcoming these kinds of things as well. And finally, enforcement. As long as we're in logging or detection mode to detect all the flows and start, annotating or locking them down, things are a bit more straightforward or easy to handle with, because it's mostly the privacy or the requirement team in these product orgs that is dealing with all of this data or the data flow violations. The moment we turn on enforcement, we're now talking about actual breakages. So how do we do this at scale where every single data flow is being checked for whether it's adhering to the policy requirement? What do we do when we have breakages without taking down the site? That has also been challenging, and this is another area of focus that we're trying to deal with over here. So that is like the high level of all the challenges that we have over here. And with that, I'll go to like some final thoughts. The tech we described here is actively used today for hundreds of different kinds of requirements. So we're using this as like the foundational infrastructure across all our services and workloads, whether it's like training for machine learning pipelines or web request serving or batch processing jobs. All of this is using policy zones for purpose limitation. Our current focus is on driving improvements. So while we have a good handle now on the developer experience and the efficiency portions, because those are the areas that we focused a lot in our earlier iterations, we're still trying to iron out the kinks in being scalable with our reclassification, being scalable with how we do enforcement without taking down the site very often, and so on and so forth. So the space, while we have been working on it for, at this point, I realize like 4 or 5 years, the space is still pretty new. And we're still dealing with a lot of these challenges as we're still in the process of successfully rolling out our type system changes and so on and so forth. With that, I will say that this infra took a village to build. Many organizations across Meta had to partner because we built the policy zones library, but we had to sit with all of these infrastructure teams to integrate these checks and do it in a performant way across the board. And special thanks to Dana and Rituraj for helping me with the content as well. With that, I think we are right on time, and I think we can move to questions.
Thank you, Amrita.